Here is something quiet to hold while you settle in. Every second that passes tonight, the distance between the farthest galaxies and our own grows a little wider than it was the second before. Not because anything is flying anywhere, but because space itself is gently and relentlessly getting bigger. And the strange part, the part that keeps physicists awake, is that no one can tell you what is doing the pushing. Tonight we will walk slowly through that mystery, the thing called dark energy, and through every confusing piece around it. Before we begin, I would love to know where you are right now and what the clock is telling you as you listen. Leave a comment with your city and your local time. I love imagining all these quiet rooms, in all these time zones, sharing one slow story. Now, let us breathe out together and begin. Good. Let your shoulders come down from wherever they have been sitting all day. There is nowhere you need to be for the next couple of hours and nothing you need to solve. You do not have to remember any of this. You do not have to follow every turn. If your attention drifts off somewhere warm and you lose the thread, that is completely fine, because the thread will still be here, moving along at the same unhurried pace, ready for you whenever you wander back. This is not a lecture you are being tested on. It is more like sitting beside a window late at night with someone who finds the universe genuinely fascinating and who is happy to talk about it softly until you fall asleep. Dark energy has a reputation. People hear the name and assume it must be impossibly difficult, the kind of thing only someone with a wall of equations could ever understand. And it is true that the deepest version of the idea lives inside very serious mathematics. But the heart of it, the actual picture, is something you can hold in your mind in the way you hold the shape of a familiar room in the dark. We are going to build that picture one small piece at a time. No leaps, no jargon dropped on you without warning. Just a slow, patient walk from things you already know toward things almost nobody fully understands. And by the end, you will not have all the answers, because no one does. But you will understand the question, and you will understand it well. So let us start somewhere ordinary. Let us start with the night sky. Think for a moment about the last time you looked up at the stars away from city lights. Maybe on a beach, or in a field, or from a window in the countryside, where the dark is properly dark. There is that first impression, the one everyone has, that the sky is a fixed thing, a ceiling, a black dome with little points of light pinned to it, holding perfectly still while you turn slowly beneath it. It feels permanent. It feels like it has always looked this way and always will. Your grandparents saw the same constellations. The ancient Egyptians watched the same bright stars rise over the same horizon. For almost the whole of human history, that was simply the truth as far as anyone could tell. The heavens were eternal and unchanging, and the only motion up there was the slow, dependable wheeling of the same lights, night after night, season after season. And here's the thing. That impression is almost completely wrong, and it took us a very long time to find out. The sky is not a fixed dome. It is not even a still picture. Every one of those faint smudges of light that we now know to be other galaxies, vast islands of hundreds of billions of stars, is drifting away from us, and not gently coasting to a stop, the way a thrown ball slows and falls. They are drifting away faster and faster as time goes on. The universe is not just expanding, it is expanding more eagerly with every passing year. Something is feeding the expansion, and that something is what we are here to understand tonight. Let me give you the central mystery in its simplest form, because everything else hangs from this one question. Imagine you toss a ball straight up into the air. You already know, in your body, what happens next. The ball climbs, it slows, it pauses for the briefest instant at the top, and then it falls back to your hand. Gravity pulls it down. That is the whole story of the ball, and it is the story we expect from anything that is thrown. It rises, it slows, it returns. For most of the 20th century, the smartest people who study the universe expected the cosmos to behave exactly like that thrown ball. The universe had been thrown outward by some enormous beginning, and it was expanding, yes. But surely gravity, the gentle inward tug of all the matter and everything, was quietly slowing that expansion down. The only real question, people thought, was whether the universe had been thrown hard enough to keep coasting outward forever, or whether gravity would eventually win and pull everything back together. Either way, the expansion should be slowing. That was obvious. That was the safe, sensible expectation that almost everyone shared. And then, near the very end of that century, a small number of careful astronomers pointed their instruments at exploding stars in the distant universe, expecting to measure exactly how much the expansion had slowed. What they found instead broke the picture open. The expansion was not slowing at all. It was speeding up. It was as if you had tossed that ball into the air, and instead of slowing and falling back, it had paused and then begun to rise faster, climbing away from your hand of its own accord, as though some invisible hand were pushing it gently but firmly toward the sky. Now think about how strange that is for a moment. A ball that rises faster the higher it goes. That is the universe we actually live in. And the invisible hand doing the pushing is the thing we now call dark energy. We will get to those exploding stars, and to the astronomers who found them, and to the long argument that followed. But to feel why their discovery landed like a thunderclap, you first need the story of how we ever learned the universe was moving at all. So let us go back, slowly, to the beginning of the last century, to a time when the entire universe, as far as respectable science was concerned, was thought to be one single galaxy holding perfectly still. The first quiet hero of this story is a man almost no one outside astronomy has ever heard of. His name was Vesto Slipher, and he worked at the Lowell Observatory in Flagstaff, Arizona, a beautiful high place where the air is thin and the nights are clear. This was around the year 1912. At that time, nobody knew what the faint, fuzzy patches of light, called spiral nebulae, actually were. Some thought they were clouds of gas inside our own galaxy, perhaps young solar systems in the making. The idea that each one might be an entire separate galaxy, as large as our own, sitting unimaginably far away, was a wild and not very respectable thought. Slipher had a tool that let him do something new. He could take the light from one of those faint spirals and spread it out into a spectrum, the way a prism spreads sunlight into a rainbow. And in that spread-out light, there are dark lines, like a barcode, that tell you which chemical elements are present and, crucially, whether the source is moving toward you or away from you. Here is the gentle idea behind it. When something that emits light moves away from you, its light gets stretched toward the red end of the spectrum. When it moves toward you, the light gets squeezed toward the blue. This is called redshift and blueshift, and it is the light equivalent of something you already know from sound, the way a passing ambulance siren drops in pitch as it goes by. The sound stretches as the ambulance moves away. Light does the same thing. So Slipher sat in the cold at his telescope, night after night, patiently gathering the dim light of these spirals and reading their barcodes. And he found something he did not expect. Almost every spiral he looked at was redshifted. Its Its light was stretched, which meant almost every one of them was moving away from us, and moving fast, far faster than anything else known at the time. By around 1917, he had measured a couple of dozen of them, and the pattern was undeniable. Out there in the dark, the spirals were fleeing. Slifer did not know why, and he could not yet say how far away they were, so he could not put the whole picture together. But he had found the first real clue. The universe was not holding still. While Slifer was measuring light in Arizona, the mathematics that would explain his measurements was being worked out, slowly and separately, by people who had never met him. The deepest of these was a Russian named Alexander Friedmann, a mathematician and physicist who took the brand new theory of gravity that Albert Einstein had published in 1915, the general theory of relativity, and asked a simple question. If you apply this theory to the whole universe at once, what does it say the universe should be doing? Einstein's theory describes gravity not as a force exactly, but as the bending and curving of space and time by matter and energy. Friedmann did the patient algebra, and around 1922 he found something that surprised almost everyone, including Einstein. The equations did not allow for a still, unchanging universe. They insisted that the universe must be either expanding or contracting. It could not simply sit there. Sadly, Friedmann died young of typhoid fever in 1925, before he could see how right he had been. A few years later, and quite independently, a Belgian came to the same conclusion and went further. His name was Georges Lemaitre, and he was something you do not often picture when you imagine a cosmologist. He was a Catholic priest. He was also a gifted physicist, and in 1927 he published a paper in a small Belgian journal that almost no one read at the time, in which he proposed that the universe is expanding, that the spirals Slifer had measured are flying apart because the space between them is growing, and even that the speed at which a galaxy recedes should be proportional to its distance. The farther away a galaxy is, the faster it should be moving away. He had, in effect, written down the law of cosmic expansion before anyone had the observations to prove it. Lemaitre went on, a few years later, to imagine running the expansion backward in time until everything was packed into a single dense beginning, what he poetically called the primeval atom. This was the first real version of what we now call the Big Bang. But the man whose name ended up on the discovery, the one most people remember, was an American working at the Mount Wilson Observatory in California, on what was then the largest telescope in the world, the 100-inch Hooker telescope. His name was Edwin Hubble. Hubble had a commanding instrument and a careful assistant named Milton Humason, and together they did two things that the others could not. First, Hubble managed to measure the distances to some of these spiral nebulae, using a clever trick involving a certain kind of pulsing star whose true brightness can be worked out from the rhythm of its pulsing. This finally proved, beyond argument, that the spirals were not clouds inside our galaxy at all. They were separate galaxies, far, far away, each one a city of stars in its own right. Our Milky Way was suddenly one island among countless others in an ocean far vaster than anyone had dared imagine. And second, when Hubble plotted the distances he had measured against the red shifts that Slifer and others had recorded, the points fell almost along a straight line. The farther away a galaxy was, the faster it was rushing from us, in just the proportion that Lemaitre had predicted. This was 1929. It was the observational proof that the universe is expanding. From that moment, the still and eternal sky was gone for good, replaced by something dynamic and astonishing. We were living inside a cosmos that was growing. Now I want to bring Einstein himself back into the room, because his role in this story is one of the most human moments in all of science, and it matters for everything that comes later. Remember that Einstein had published his theory of gravity in 1915. When he applied it to the whole universe in 1917, before any of these expansion measurements existed, he ran into a problem that bothered him deeply. His own equations, just as Friedman would later confirm, refused to give him a stable, unchanging universe. Left alone, the matter in the cosmos would pull itself together and collapse. And like nearly everyone of his generation, Einstein believed the universe was static, eternal. The same yesterday, today, and forever. So he did something he would come to regret. He added an extra term to his equations by hand, a kind of fudge factor, a gentle outward push built into the fabric of space itself, finely tuned to exactly balance the inward pull of gravity and hold the universe perfectly still. He gave this term a name. He called it the cosmological constant, and he represented it with the Greek letter lambda, which looks a little like an upside-down letter Y. Sit with that for a moment, because it is going to matter enormously. As early as 1917, Einstein had written into his theory the idea that empty space might carry a built-in tendency to push outward, an energy belonging to space itself, smooth and even, present everywhere. He did it for the wrong reason. He did it to keep the universe still. But the mathematical seed was planted. Then Hubble's results arrived. The universe was not static after all. It was expanding exactly as Friedman and Lemaitre had said it must, and exactly as Einstein's untouched equations had originally tried to tell him before he added his fudge factor to silence them. Einstein was, by all accounts, dismayed. He removed the cosmological constant from his equations and, according to the physicist George Gamow, who told the story years later, called it the biggest blunder of his life. We should be honest and say that historians are not certain Einstein ever used those exact words, and the phrase may have grown in the telling. But the feeling behind it was real. He had patched his beautiful theory to fit a belief about the universe that turned out to be false. And in doing so, he had missed the chance to predict the expansion himself. He buried the cosmological constant and tried to forget it. Here is what is so quietly remarkable about all of this. That blunder, that embarrassing little term that Einstein wished he had never written down, is the very thing that, 70 years later, would come roaring back to explain the strangest discovery in modern astronomy. The idea he threw away is at the center of the mystery we are unwinding tonight. But to understand how it returned, we first need to slow down and really feel what it means for the universe to expand at all. Because almost everyone, when they first hear the word expansion, pictures it wrong. When you hear that the universe is expanding, the natural picture that forms in your mind is something like an explosion. A bomb goes off at some central point, and bits of debris go flying outward in all directions, away from the place where it started. So you imagine the galaxies as shrapnel from a great blast, hurtling outward through space, leaving an empty center behind them. It is a vivid picture, and it is almost entirely wrong. There is no center. There is no edge that the galaxies are flying away from. The galaxies are not really moving through space at all, not in the way a thrown stone moves through the air. Instead, the space between them is growing. Let me say that again, slowly, because it is the single most important idea in this whole subject. And once it clicks, a great deal of the confusion melts away. The galaxies are not flying apart through space. The space itself, the distance, the emptiness between them, is being created and stretched. This is genuinely hard to picture. So let me give you the analogy that astronomers reach for, and then a second one, because between the two of them, the idea usually settles. Imagine you are making a loaf of raisin bread. Before it goes in the oven, you have a lump of dough with raisins dotted all through it. Now the dough begins to rise. As it rises, it swells in every direction at once. And here is the lovely thing to notice. Every raisin moves away from every other raisin. Pick any single raisin and pretend you are sitting on it. From where you sit, every other raisin in the loaf is drifting away from you. The nearby raisins drift away slowly. The faraway raisins, with much more dough swelling up between you and them, drift away much faster. That is exactly Hubble's law. The farther a raisin is, the faster it recedes. And notice crucially that no raisin is special. There is no center raisin that everything is fleeing from. Sit on any raisin you like, and you will see the same thing. Everything moving away, the distant ones fastest. The dough is not exploding from a point. It is simply growing everywhere, all at once, and carrying the raisins along for the ride. The galaxies are the raisins. Space is the dough. And just as the raisins themselves do not swell, the galaxies themselves are not getting bigger. And you yourself are not getting bigger. And the Earth is not getting bigger. Because within a galaxy, and within your body, gravity and the other forces that hold things together are far stronger than the gentle stretching of space. The stretching only wins out on the largest scales, in the vast, empty gulfs between galaxies, where there is nothing to hold them in place. So it is only across those enormous distances that the expansion shows itself. Now here is where we can finally understand what Slipher's redshift really was. We said earlier that light from a receding object gets stretched toward the red. But if the galaxies are not so much moving through space as being carried apart by growing space, then there is an even more beautiful way to see it. The light itself, traveling across that growing space on its long journey to us, gets stretched along with everything else. Picture a wave of light leaving a distant galaxy billions of years ago. As it crosses the vast and growing gulf between that galaxy and us, the space it is traveling through swells, and the light wave swells with it. Its peaks and troughs drawn farther apart until by the time it arrives at our telescope, it has been stretched toward the red. The redshift is not really the galaxy shouting at us as it speeds away. It is the fingerprint of all the space the light has crossed, all of it gently growing during the light's long voyage. The farther the light has traveled, the more space it has crossed, the more stretching it has picked up, and so the more redshifted it appears. When you measure a galaxy's redshift, you are, in a real sense, measuring how much the universe has expanded since that light set out. Let me try a second picture, just to be sure this lands. Because I know this is the place where people's eyes can start to glaze. Imagine an enormous balloon, and on its surface you have drawn dots with a marker, each dot a galaxy. Now you begin to inflate the balloon. The rubber surface stretches. Every dot moves away from every other dot. There is no special dot at the center of the surface, because the surface of a balloon has no center on it. And if you drew a little wiggly line on the rubber to represent a light wave, that wiggle would stretch wider as the balloon grew, just like our red-shifted light. The only thing you must do to make the analogy honest is to forget about the inside of the balloon and the air and the rubber, and pretend that the two-dimensional surface is the entire universe, all there is. Hard to do, I know. But the lesson survives. Expansion is the swelling of the thing the galaxies live in, not a flight through some fixed and pre-existing space. There is one more gentle idea to add here before we go deeper, and it is a comforting one. Because the expansion is the stretching of space itself, there is no speed limit on how fast distant things can recede. You may have heard that nothing can travel faster than light, and that is true for anything moving through space. But the expansion of space is not a thing moving through space. It is space being created. And so galaxies that are far enough away from us are being carried apart faster than light can travel, simply because there is so much growing space between us and them. Their light, in some cases, will never reach us at all, because the space it would have to cross is growing faster than the light can swim across it. This is not science fiction. It is a quiet, established part of how our universe works. There are galaxies whose light is, this very night, setting out toward us and losing the race, falling forever behind the swelling tide of new space. So that is expansion. Space growing, galaxies carried along, light stretched on its journey, the most distant ones outrunning us forever. For decades after Hubble, this was the picture, and the great question that remained was simply one of pace. The expansion was happening, but how was it changing over time? Was it slowing down, as everyone expected, speeding up, as no one expected, or holding steady? To answer that, you have to do something much harder than measuring how fast galaxies are moving away today. You have to measure how fast they were moving away long, long ago, and compare. And that, as we will see, is where the exploding stars come in. But before we get there, we need to spend some time with gravity, and with the strange idea that empty space might not be empty at all. Let us think about gravity for a while, gently, because gravity is the reason everyone expected the expansion to be slowing, and you cannot feel the shock of the real answer until you feel how reasonable that expectation was. Gravity, as you know it in everyday life, only ever pulls. Drop a spoon and it falls toward the floor. The moon is held in its loop around the earth by the earth's pull. The earth is held in its loop around the sun by the sun's pull. Everything with mass tugs on everything else with mass, always inward, always trying to draw things together. There is no everyday experience of gravity pushing anything apart. It is the great gatherer. It builds stars by pulling gas together until it ignites. It builds galaxies by pulling stars and gas into great spinning wheels. So when astronomers looked at a universe full of matter, full of galaxies and gas and dust, all of it gravitationally tugging on all the rest, the conclusion seemed inescapable. All that mutual pulling should be acting as a brake on the expansion, slowing it year by year, just as the Earth's pull slows a thrown ball. The universe was expanding, yes, but gravity should be patiently reining it in. The only open question, people thought, was who would win the long contest between the outward motion and the inward pull. If the universe contained enough matter, gravity would eventually halt the expansion entirely and then reverse it, drawing everything back together in a great collapse that some called the Big Crunch, the Big Bang, played in reverse. If the universe contained too little matter, gravity would never quite win, and the expansion would coast outward forever, ever slowing but never stopping. And right on the knife edge between those two fates lay a third possibility. A universe perfectly balanced, slowing forever toward but never reaching a stop. For most of the 20th century, the entire field of cosmology was essentially an effort to measure how much matter the universe held, in order to learn which of these three slowing futures was ours. Notice the unspoken assumption underneath all three. In every one of them, the expansion is slowing. The only argument was about how much. Now I want to take you carefully to the heart of the strangeness, and I am going to ask you to hold a single odd idea in your mind, just for a moment, before I explain it. Here it is. What if empty space is not empty? What if the vacuum, the nothing between the galaxies, the perfectly clean dark gap where there are no atoms, no light, no dust, nothing at all? What if that nothing carries energy of its own? Just by being space, just by existing. I know how that sounds. It sounds like a contradiction, energy and emptiness. So let us slow right down and build it up honestly, because this is the idea that everything turns on. In the older, simpler picture of the world, energy is something carried by stuff. A moving car has energy. A hot cup of tea has energy. Light has energy. The sun pours energy across space. Energy belongs to things, and where there are no things, there is no energy. By that logic, a box of perfect vacuum should contain exactly nothing, no energy whatsoever. But the deeper theory of how the world works at the smallest scales, the theory we call quantum physics, paints a stranger picture of the vacuum. According to it, empty space is not a calm, dead nothing. It is a restless, simmering thing, filled with a constant flickering of energy, with pairs of particles briefly appearing and vanishing again, too quickly to ever be caught. The vacuum, in this view, has a kind of baseline hum, a lowest possible energy that it can never quite switch off, even when every particle and every ray of light has been removed. We call this the energy of the vacuum, or sometimes the zero-point energy, the energy that remains at the very bottom, when there is nothing left to take away. Here is why this matters so much for the universe as a whole. If empty space carries some amount of energy, and if that energy is the same in every patch of empty space, smooth and even everywhere, then something peculiar happens as the universe expands. When the universe grows, you do not get the same vacuum spread thinner. You get more vacuum, more cubic meters of space, each one carrying its own little portion of vacuum energy. The energy of empty space does not dilute as the universe expands, the way a cloud of gas thins out as it spreads. Instead, the total amount of it grows, because there is more space to hold it. Think about that for a moment. Ordinary matter thins out as the universe grows, so its inward gravitational pull gets weaker over time. But the energy of empty space stays at the same strength in every region, no matter how much the universe stretches. So as the universe gets bigger and emptier, matter fades into the background, and the energy of the vacuum, steady and undiluted, comes to dominate. And now for the truly counterintuitive part, the part that takes us right back to Einstein's discarded fudge factor. In Einstein's theory of gravity, it is not only mass that bends space and pulls things together. Energy bends space too, and so does pressure. Most things we know have positive pressure, the outward push of a gas in a balloon, of steam in a kettle. But the energy of empty space, when you work through the mathematics, behaves as though it has negative pressure, a kind of inward tension, like a stretched rubber sheet pulling on itself. And here is the strange gift that Einstein's equations hand us. Within the theory of general relativity, a substance with strong enough negative pressure does not pull space together. It pushes space apart. Negative pressure, spread evenly through the vacuum, acts as a repulsive form of gravity. It is gravity, but in reverse, gravity that shoves rather than gathers. This is the cosmological constant, returning in its true form. When Einstein added that term in 1917 to hold the universe still, what he was really adding, whether he fully realized it or not, was exactly this: an energy belonging to empty space with a repulsive gravitational effect, finely balanced to oppose the inward pull of matter. He used it to prop up a static universe and then threw it away, when the universe turned out to be expanding. But the term itself never went away. It sat quietly in the equations, switched off, set to zero, waiting. And the question that hung over cosmology, mostly unasked for decades, was simple. Is the cosmological constant really zero? Is the energy of empty space really nothing? Or is it some small but not quite zero amount, faint enough that we had never noticed it, but real enough that, given a vast and aging universe, it might one day win? I want to give that idea a plainer name before we move on, because we will be using it for the rest of the night. The energy of empty space, the cosmological constant, the thing with negative pressure that pushes space apart. This is one leading candidate for what we now call dark energy. The word dark here does not mean black or sinister. It simply means hidden, invisible, something we detect only by its effects, not by any light it gives off. Dark energy is the umbrella name for whatever it is that is causing the expansion of the universe to speed up. The energy of the vacuum is the simplest guess at what that whatever might be. But as we will see, it is a guess riddled with its own deep and embarrassing problems. And there are rival guesses too. For now, just hold the shape of the idea. Empty space, possibly, carries a faint, steady energy that pushes outward, and as the universe grows emptier, that push has more and more room to take over. Keep that in mind, because when the exploding stars finally tell their story, this is the idea that will be waiting to catch what they reveal. I promised you an analogy for the strangest part of all this. The idea that something with negative pressure could push the universe apart. And I want to give it to you now. Slowly, because this is the one place where ordinary intuition genuinely fails. And the honest thing to do is to admit that, and then build a bridge across the gap. Picture a very large, very old house with many rooms, and imagine that the air in this house is not ordinary air. Imagine that the empty space in every room carries a faint, even glow, a soft pressure that presses outward against the walls. The same in every room, in every corner, in every cubic foot of emptiness. Now here is the trick that makes it unlike anything you have ever felt. In a normal house, if you knock down a wall and make a room bigger, the air spreads out and thins, and its push on the remaining walls gets weaker. But in this house, the glow does not thin when you make a room bigger. Every new cubic foot of empty space you create comes already filled with the same glow at the same strength. So the bigger you make the house, the more glow there is in total, and the harder it presses outward, and the more the walls want to keep moving out. The expansion feeds itself. More space means more of the outward stuff, which makes more space, which makes more of the outward stuff. You can feel, in that runaway loop, why the expansion does not slow but accelerates. That is the heart of it. But I have been a little loose on purpose to give your intuition something to hold. The word pressure has been doing the work of the word push in that picture. And in real physics, those two things come apart in a way that is almost impossible to feel in your body. In Einstein's theory, it is not the outward pressure of the vacuum that drives the expansion. It is something deeper and stranger. Gravity, in general relativity, responds not just to energy but to pressure. And a positive pressure actually adds to gravity's inward pull. The vacuum, oddly, has negative pressure, an inward tension rather than an outward shove. And it is precisely that negative pressure, fed into Einstein's equations, that flips gravity around and turns it repulsive on the largest scales. I am telling you this not to confuse you, but to be honest with you. Because there is a temptation in stories like this to pretend everything maps neatly onto a cozy household picture, and it does not. The truth is that the push of dark energy is not really a push at all in the way a hand pushes a door. It is a feature of the geometry of space and time, a consequence of how energy and tension warp the fabric of the cosmos. The glowing house gets you most of the way there. It gets you the crucial idea that the outward effect does not dilute as space grows, and so it takes over in the end. Beyond that, the only fully honest description lives in the mathematics, and you do not need the mathematics tonight. You need the shape, and the shape is this: a faint property of empty space, undiluted by expansion, gently turning gravity inside out across the great gulfs of the cosmos, until the universe is not coasting to a stop, but quietly accelerating outward. Hold the glowing house. Let the rest go, and let us return to the astronomers, because it is almost time for the exploding stars. To measure how the expansion of the universe has changed over time, you need a very particular kind of object. You need something far away, so far that its light has been traveling for billions of years and therefore shows you the universe as it was long ago. And you need that something to have a known, reliable brightness, so that by comparing how bright it truly is with how bright it appears from here, you can work out exactly how far away it sits. Astronomers call such an object a standard candle. If you know that every candle of a certain make burns with exactly the same true brightness, then a dim one must be far and a bright one must be near, and the dimness tells you the distance with real precision. For a long time, the trouble was that the things bright enough to be seen across billions of light years, like whole galaxies, are not standard at all. Galaxies come in wildly different sizes and brightnesses, so a faint one might be small and close or large and very far, and you cannot tell which. What astronomers needed was a kind of cosmic beacon that always shone with the same power, every single time, no matter where in the universe it appeared. And nature, it turns out, provides exactly such a beacon in one of the most violent events there is. A particular kind of exploding star, called a Type 1, a supernova. Let me tell you what one of these is, because it is genuinely beautiful in its reliability. Out in the galaxy, there are dense, burnt-out cores of dead stars called white dwarfs, each one about the size of the Earth, but carrying nearly the mass of the Sun, packed so tightly that a spoonful would weigh tons. A white dwarf on its own just sits there, slowly cooling for ages. But if a white dwarf has a companion star close by, it can siphon material off that companion, gathering mass onto itself, growing heavier and heavier. And here is the lovely part. There is a precise limit, a specific mass, beyond which a white dwarf simply cannot hold itself up against its own gravity. That limit is about 1 4/10 times the mass of the Sun, and it was first worked out by a young physicist named Subramanian Chandrasekhar in the early 1930s. When a white dwarf reaches that exact tipping point, it detonates, blowing itself apart in a thermonuclear explosion that briefly outshines an entire galaxy of billions of stars. Now think about why that precise limit is such a gift. Because every one of these supernovae goes off at very nearly the same mass, in very nearly the same way. Each one releases very nearly the same amount of light. They are nature's standard candles, scattered across the whole history of the universe. Each one a beacon of known true brightness, briefly bright enough to be seen across billions of light years. Measure how bright one appears. Compare it to how bright you know it truly is, and you have its distance. Measure the redshift of the galaxy it exploded in, and you have how much the universe has expanded since that light set out. Gather enough of them, near and far, recent and ancient. And you can chart the entire expansion history of the cosmos and finally answer the great question. Is the expansion slowing, as everyone expected, or doing something else? In the 1990s, two separate teams of astronomers set out, in a quiet sort of rivalry, to do exactly this. The first was called the Supernova Cosmology Project, led by a physicist named Saul Perlmutter, working out of the Lawrence Berkeley National Laboratory in California. The second was called the High Redshift Supernova Search Team, led by an Australian-based astronomer named Brian Schmidt, with a young and brilliant member named Adam Rees doing much of the crucial analysis. Both teams faced the same brutal difficulty. Type 1, a supernovae, are rare in any one galaxy, going off perhaps once or twice a century, and they fade within weeks. To catch enough distant ones, the teams had to photograph huge patches of sky containing thousands of galaxies, then photograph them again weeks later, and computer compare the images to spot the new points of light that had not been there before. Then they had to scramble to point the world's largest telescopes at each fresh supernova before it faded, to measure its brightness and its redshift. It was painstaking, anxious, competitive work, carried out over several years, with both teams quietly racing toward the same prize. And both teams expected the same answer. They expected to find that distant supernovae, the ancient ones, would appear slightly brighter than you would guess in a coasting universe. Because in a universe that had been slowing down, those distant objects would be a little closer than a simple calculation suggested. That was the sensible prediction. Gravity slows the expansion, so the distant past should show a faster, more crowded universe. Everyone was really just arguing about how much slowing there had been. What they found instead, both teams independently around 1998, was the opposite. The distant supernovae were not brighter than expected. They were fainter. Fainter means farther away than they should be in any slowing universe, farther even than in a universe coasting at a steady rate. The only way to make the numbers work was almost too strange to say out loud. The expansion of the universe had not been slowing down at all. For the last several billion years, it had been speeding up. The galaxies were not coasting toward a gentle stop. They were accelerating apart, pushed by something invisible, something that filled all of space and pressed it outward, exactly the kind of thing that Einstein's discarded cosmological constant described. I want you to feel how unwelcome this discovery was, because that is part of what makes it so trustworthy. Neither team wanted this answer. They checked it again and again, hunting for some error, some dust between us and the supernovae that might be dimming them and faking the result. Some way in which ancient supernovae might be intrinsically different from modern ones. Brian Schmidt later described his reaction as something between amazement and alarm, a worry that they had made some terrible mistake. Adam Rees found the acceleration in his analysis and at first assumed it must be a bug. But the two teams had worked separately, with different supernovae, different telescopes, different methods. And they arrived at the same impossible conclusion at almost the same moment, when two rival groups who would have loved to prove each other wrong instead confirm each other's strangest result. Science sits up and pays attention. The acceleration of the universe was announced in 1998 and 1999, and it landed like a quiet earthquake. It meant that roughly 70% of everything, of all the energy in the entire cosmos, was made of this unknown, unseen, space-filling stuff that pushes outward. Not stars, not gas, not the mysterious dark matter that holds galaxies together, but something else again, something even more mysterious, woven into the vacuum itself. A journalist and a cosmologist soon gave it the name that stuck: dark energy. And in 2011, more than a decade after the discovery, Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel Prize in Physics for revealing that we live in an accelerating universe. 3 people, 2 teams, a few hundred exploding stars, and a result that turned cosmology upside down and handed Einstein's biggest blunder back to him as one of the deepest truths in nature. But here is the thing, and it is the thing that keeps this from being a tidy story with a happy ending. Discovering that dark energy exists and measuring how much of it there is did not tell us what it actually is. We learned that the cosmological constant is not 0. We learned that empty space behaves as though it carries energy. But when physicists tried to calculate, from their best theories, how much energy empty space should carry, they ran headlong into a problem so enormous and so embarrassing that some have called it the worst prediction in the history of science. And that is where we go next, slowly, into the strange gap between what the universe is doing and what our theories say it ought to be doing. Let us slow right down for this part, because it is one of the most genuinely astonishing facts in all of physics, and it deserves to be unwrapped gently rather than rushed. We said that the simplest idea for what dark energy might be is the energy of empty space, the vacuum energy, the faint, steady hum that quantum physics says fills all of nothing. That is a lovely idea, and it fits the observations in shape. The vacuum energy does not dilute as the universe expands. It has the right kind of repulsive effect, and it matches the smooth, even, everywhere quality that dark energy seems to have. So far, so good. The trouble begins the moment you try to calculate how much vacuum energy there ought to be. Because quantum physics does not just say the vacuum has some energy. It lets you estimate how much. And when physicists do that estimate, using the same quantum field theory that has been tested to staggering precision in particle accelerators, the same theory that correctly predicts the behavior of electrons and light to more decimal places than almost anything else we know, they get an answer. And the answer is wrong. Not a little wrong. Not wrong by a factor of 2 or 10 or 1,000, the sort of disagreement scientists argue about and eventually resolve. The predicted amount of vacuum energy is larger than the amount we actually observe by a number so large it is hard to even speak aloud. Depending on exactly how you do the calculation, the theory overshoots reality by something like a 1 followed by a great many zeros, often quoted as around 120 zeros. Let me try to give you a feeling for a number like that, though honestly, nothing really can. If you took every grain of sand on every beach and in every desert on the entire planet, and then imagined a number of grains far, far beyond even that, you would still not be close. The mismatch between what our best theory predicts for the energy of empty space and what the universe actually contains is the single largest discrepancy between theory and observation anywhere in physics. People sometimes call it, with a kind of rueful affection, the worst prediction in the history of science. And it is not a fringe theory making this prediction. It is the very framework that underlies all of modern particle physics. The framework that works so beautifully everywhere else. Sit with how uncomfortable that is. Our best theory of the small says empty space should be unimaginably, catastrophically full of energy. So full that it would have blown the young universe apart instantly and prevented any galaxies or stars or planets from ever forming. And yet, here we are, in a universe with a faint, gentle, almost vanishing whisper of dark energy, just enough to nudge the expansion into a slow acceleration over billions of years, but so small compared to the prediction that it is as if some unknown mechanism had taken that monstrous predicted energy and canceled almost all of it away, leaving behind only the tiniest sliver. Not exactly zero, which we might at least be able to explain with some clean principle. But not the huge predicted value either. Something absurdly, precisely, mysteriously small. This is called the cosmological constant problem, and it has hung over physics for decades. No one has solved it. Some of the finest minds of the last half-century have broken themselves against it. It may be the deepest unsolved puzzle in all of fundamental science, and dark energy sits right at its center. So you can see why some physicists are uneasy about saying that dark energy simply is the vacuum energy, the cosmological constant, and leaving it there. Yes, the cosmological constant fits the observations beautifully. But pointing at it and saying that is the answer feels, to many, like writing down a number you cannot explain and refusing to look at the impossible theory that is supposed to predict it. It works, but it does not satisfy. And so, alongside the cosmological constant, people have invented other ideas about what dark energy might be, hoping that one of them might be both correct and explicable. The most popular of these alternatives has a wonderful old name. It is called quintessence. The word comes from the ancient and medieval idea of a fifth element. The Greeks, following Aristotle, believed everything on Earth was made of 4 elements: earth, water, air, and fire. But that the heavens, the perfect unchanging realm of the stars, must be made of a fifth, finer substance, a quintessence, the fifth essence. Modern physicists borrowed the word a little playfully for a particular new idea about dark energy. Here is the difference that matters. The cosmological constant is, by definition, absolutely constant. The energy of empty space, in that picture, has the same value everywhere and at every moment, fixed, eternal, unchanging since the beginning and unchanging until the end. Quintessence imagines something subtly different. It imagines that dark energy is not a fixed property of space, but a kind of invisible field, spread through the universe, a field whose strength can slowly change over time, and perhaps even vary slightly from place to place. If dark energy is a constant, then it has always been there at the same strength. Even in the early universe, when it was utterly overwhelmed by the dense, hot matter of the young cosmos, only emerging to dominate much later as matter thinned out. But if dark energy is quintessence, a slowly shifting field, then its strength today might be different from its strength long ago, and crucially, its strength tomorrow might be different again. It might be gently fading. It might be gently growing. It might one day switch off or reverse. That is a profoundly different future from the eternal, steady push of a true constant. And so distinguishing between these two pictures, a fixed cosmological constant on the one hand and a changing quintessence field on the other, is not just academic hair-splitting. It is, quite literally, the difference between knowing the fate of the universe and not knowing it. Physicists have a clever way of capturing this difference in a single number, and I want to give it to you, gently, because you will hear it mentioned and it is good to know what it means. They ask about the relationship between the pressure of dark energy and its energy, and they wrap that relationship up in a quantity they simply call W, the letter W. For a pure cosmological constant, the energy of empty space, this number W has the exact value of -1. Precisely -1. No more, no less, never changing. If dark energy is instead some form of quintessence, then W might be a little different from -1, perhaps slightly above it, and it might drift over time rather than holding fixed. So when you hear that astronomers are trying to measure whether W is exactly -1 or just close to it, and whether it stays put or changes, what they are really asking is whether dark energy is the simple, eternal constant or something stranger and more alive. A value of exactly and forever -1 means a true cosmological constant. Anything else means the deeper story is still hiding from us. For a long time, all the measurements pointed stubbornly at W being -1, or so close to it that no one could tell the difference. The simple cosmological constant kept winning, however unsatisfying it felt. The universe seemed content to be described by Einstein's discarded term, a flat, featureless energy of empty space, and the dream of finding something richer, something that might actually be explainable, kept coming up empty. The standard model of cosmology settled into place, with the cosmological constant at its heart, and for the better part of 2 decades, it fit the data almost too well. But measurements get better. Telescopes get larger. Maps of the universe grow more detailed. And in the last few years, very recently, the picture has begun, just possibly, to shift. We will come to that, because it is the freshest, most uncertain part of the whole story. But first, let us take what we have learned so far and assemble it into the single picture that cosmologists actually use to describe the universe, so that you can see where dark energy fits among everything else. Before we do, though, I can imagine a small doubt forming somewhere in the back of your mind, and it is a fair one, so let me answer it gently. We have been talking as if empty space really does carry energy, as if the vacuum really is this restless, simmering thing rather than a plain and honest nothing. And you might quietly wonder whether that is just a story physicists tell, a mathematical convenience, or whether there is any actual evidence that empty space behaves this way. It turns out there is, and it comes from a small and elegant experiment that you can almost picture on a kitchen table. Back in 1948, a Dutch physicist named Hendrik Casimir was thinking carefully about the quantum picture of the vacuum. The idea that even perfectly empty space is filled with a constant flickering of tiny fluctuations, a kind of restless sea of possibility. And he realized that this picture made a strange and testable prediction. Imagine you take 2 flat metal plates, perfectly clean, and you bring them very, very close together in a vacuum, closer than the width of a hair, almost but not quite touching. Casimir worked out that the restless fluctuations of the vacuum would be slightly different in the narrow gap between the plates than in the open space outside them. There would be a little less of that vacuum energy squeezed into the gap than pressing in from outside, and so the plates would feel a faint pressure, a gentle push, nudging them together, caused by nothing at all, caused by the energy of empty space itself being slightly thinner between them than around them. Think about how astonishing that claim is. 2 plates, with nothing between them, no charge, no magnetism, no air, no force of any ordinary kind, and yet they are pushed together by the structure of the vacuum, by the energy of the nothing itself. For a long time, it was only a prediction, too delicate to test. But the measurement gradually became possible, and toward the end of the 20th century, careful experiments confirmed it. Physicists really did detect that faint force in just the amount Casimir had calculated half a century earlier. The vacuum, it turns out, is genuinely not empty. It really does carry energy. It really does press and push in measurable ways. The restless sea is real. And here is why I wanted to tell you this before we go further. It makes the great embarrassment of dark energy even sharper, even stranger, because the vacuum energy is not some made-up idea that we could simply discard to make the problem go away. We have measured it. We know it is there. The quantum picture of empty space passes its laboratory tests with flying colors. And yet, when we take that same well-tested picture and ask it to predict the energy of empty space on the scale of the whole universe, It gives us that monstrous wrong answer, too large by a number with 120 zeros. So we are left in the most uncomfortable position imaginable. The theory is right where we can test it closely and catastrophically wrong where we apply it to the cosmos. And we do not know why. The thing that pushes Casimir's plates together is somehow related to the thing that pushes the whole universe apart. And the bridge between the small measurement and the vast one is broken in a way no one has been able to repair. Hold that quiet discomfort lightly as we move on, because it is the truest single sentence I can offer you about dark energy. We have touched it in the laboratory, and we have watched it in the sky, and we still cannot make the two agree. Let us take a breath and gather the pieces. We have a universe that is expanding, that began in a hot, dense state long ago, and whose expansion is speeding up under the influence of something we call dark energy. Cosmologists have folded all of this into a single working description of the cosmos, and it has a slightly clumsy name. It is called the lambda cold dark matter model, and you will sometimes hear it shortened to its initials. But let us just call it the standard model of the universe. The lambda in the name is that same Greek letter Einstein used, standing for the cosmological constant for dark energy. The cold dark matter is the other invisible ingredient. And together, these two unseen things, plus the ordinary matter we are made of, make up the whole recipe. Here is the recipe, and it is humbling. Everything you have ever seen, everything that gives off or reflects light, every star, every planet, every galaxy, every cloud of glowing gas, all the atoms in your body and in the chair beneath you and in the air you are breathing, all of it together makes up only about 5% of the energy of the universe. 5%. The ordinary matter that we once thought was everything turns out to be a thin garnish on top. About another 27% is dark matter, a kind of invisible matter that does not shine and does not interact with light at all, but which has ordinary gravity, ordinary inward pull, and which holds galaxies together and shapes the great web of cosmic structure. And the remaining 68%, the largest share by far, nearly 7/10 of everything, is dark energy, the mysterious outward pressure of empty space. So the universe is, by this accounting, roughly 2/3 an unknown force we cannot explain, 1/4 an unseen matter we cannot identify, and a mere sliver of the familiar stuff that we, and everything we have ever directly observed, are made of. We live in the bright foam on top of a dark and unknown ocean. I want to pause here to clear up a confusion that catches almost everyone, because the names are so similar. Dark matter and dark energy sound like cousins, like two versions of the same thing. They are not. They are profoundly different. And keeping them apart in your mind is one of the most useful things you can take from tonight. Dark matter is matter. It has mass. It has gravity that pulls inward like all gravity. It clumps together. It gathers in halos around galaxies. It helps build structure. If anything, dark matter is on the side of gravity, helping to gather things, and in principle, to slow the expansion. We call it dark only because it gives off no light and we cannot see it directly. Dark energy is the opposite in almost every way. It does not clump. It is perfectly smooth, the same everywhere. And instead of pulling inward, it pushes outward. It does not help build galaxies. It pulls the universe apart. The only thing the two share is the word dark, meaning hidden, and the embarrassing fact that we do not really know what either of them is. But they are not relatives. One is invisible stuff that gathers. The other is an invisible tension that scatters. Hold them apart. And a great deal of the confusion around modern cosmology gently dissolves. Now, you might reasonably ask how anyone could possibly be confident about a recipe like this. About the precise claim that the universe is 5% ordinary matter, 27% dark matter, and 68% dark energy. It sounds like the kind of thing that could only be a wild guess. And yet these numbers are pinned down remarkably well from several completely different directions that all agree. The exploding stars, the supernovae, told us about the acceleration and therefore about the dark energy. The motions of galaxies and the way they cluster told us about the dark matter. And there is a third great source of evidence, perhaps the most beautiful of all. And it is something I would like to describe to you softly, because it is a kind of light from the dawn of time. When the universe was very young, only a few 100,000 years old, it was so hot and dense that it glowed, filled everywhere with a fog of light and matter all jumbled together, far too hot for atoms to even hold themselves together. Then, as the universe expanded and cooled, there came a moment when it had cooled just enough for the first atoms to form. And suddenly the fog cleared, and light was set free to travel across the cosmos. That ancient light is still traveling today, after billions of years, stretched by all that expansion from a fierce glow into a faint whisper of microwaves, filling all of space, coming from every direction. It was discovered, almost by accident, in 1965, by two scientists at a laboratory in New Jersey named Arno Penzias and Robert Wilson, who at first thought the persistent hiss in their antenna was caused by pigeon droppings, and only slowly realized they were hearing the afterglow of creation itself. We call it the cosmic microwave background. The oldest light there is, a baby picture of the universe. And here is why it matters for our story. That ancient light is not perfectly smooth. It carries within it the faintest pattern of hotter and cooler patches, the seeds of all the structure that would later grow into galaxies. By measuring that pattern with extraordinary precision, using satellites lofted above the atmosphere, cosmologists can read off the ingredients of the universe with stunning accuracy, like a baker tasting a finished loaf and deducing the exact recipe. The pattern in that ancient light only comes out right if the universe contains about 5% ordinary matter, about 27% dark matter, and about 68% dark energy. The same recipe that the supernovae pointed to, and the same recipe that the clustering of galaxies points to, comes shining out of the oldest light in existence, measured in a completely independent way. When three utterly different methods, exploding stars, clustering galaxies, and the afterglow of the Big Bang, all hand you the same answer, you begin to trust the answer. Even when the answer is as strange as a universe that is mostly made of things you cannot see or explain. That is the state of our knowledge. We know the recipe with real confidence. We simply do not understand two of the three ingredients. There is one more puzzle worth setting gently beside all this, because it deepens the mystery rather than resolving it, and it has a quietly unsettling quality that fits the late hour. Dark matter thins out as the universe expands, because it is matter and it dilutes. Dark energy does not thin out, because it belongs to space itself. So through almost all of cosmic history, one of these two has overwhelmingly dominated the other. In the early universe, matter ruled dense and thick, and dark energy was a negligible whisper. In the far future, dark energy will rule completely, and matter will be diluted into near nothingness. The strange thing is that we happen to live at the brief moment in between, the cosmic dusk when the two are roughly comparable, when matter has thinned just enough and dark energy has risen just enough that they are nearly in balance, and the universe is tipping from one era into the other. Why us? Why now? out of the entire vast span of cosmic time? Why do we find ourselves alive at precisely the rare crossover moment when the two great unseen ingredients are passing each other in the night? Physicists call this the coincidence problem, and no one knows whether it is a deep clue or just an accident of when conscious creatures happen to evolve. But it is a lovely and slightly haunting thing to consider, that we are watching the universe from its turning point. There is a particular branch of this mystery that I find especially worth lying awake over, gently, and it concerns not what dark energy is, but why it has the tiny size that it does. We said the great embarrassment of the cosmological constant problem is that empty space ought, by our best theories, to carry an enormous energy, and yet it carries only a faint sliver. Now, you might think the cleanest resolution would be for the answer to be exactly zero, for some deep and elegant principle to forbid the vacuum from having any energy at all. Physicists would actually be more comfortable with that. A clean zero often hides a beautiful symmetry, a reason. But zero is not what we measure. We measure something small and yet definitely not nothing. A value that seems almost arbitrarily, almost suspiciously fine-tuned to be just large enough to matter and just small enough not to wreck everything. One physicist, Steven Weinberg, who was among the greatest of his generation, offered a startling line of thought about this back in the late 1980s, before dark energy had even been discovered. He pointed out something simple and unsettling. If the energy of empty space had been much larger than it actually is, then in the early universe its outward push would have been so strong that matter could never have gathered together. Galaxies would never have formed. Stars would never have lit. Planets would never have cooled. And there would be no one anywhere to wonder about any of it. The very fact that we exist, that there are creatures here capable of measuring the cosmological constant, requires that the cosmological constant be small, not zero necessarily, but small enough to permit galaxies, and therefore stars, and therefore the slow chemistry of life. Weinberg used this reasoning to suggest, years in advance, that the energy of empty space, if it was not zero, ought to be small, but not vanishingly so, roughly in the range that was later actually found. Now, this line of thought has a name, and it is one that makes some physicists uneasy. It is called anthropic reasoning, reasoning from the fact of our own existence. And it usually comes paired with an even larger and stranger idea, the idea that our universe might be only one of an immense, perhaps infinite, collection of universes, each with its own value for the energy of empty space, most of them either so large that nothing forms or so negative that they collapse at once, and only a rare few, like ours, balanced in the narrow window where galaxies and stars and observers can arise. In that picture, there is no deep reason why our cosmological constant has the value it does, any more than there is a deep reason why you happen to live on a planet at a comfortable distance from its star. It is simply that the universes hostile to life have no one in them to ask the question, and the rare, hospitable ones do. We find ourselves in a friendly universe, because only friendly universes contain finders. I am not telling you this is the answer. Many physicists dislike it intensely because it seems to give up on explanation, to replace a why with a shrug and a vast, unobservable multitude of other worlds we can never check. Others think it may be the only honest way to make sense of a number that no clean principle has ever managed to explain. The truth is that nobody knows. This is one of those places where the frontier of human understanding dissolves into genuine fog, where brilliant and careful people simply disagree, and where the most honest thing anyone can say is that the smallness of dark energy is, right now, a mystery we have not cracked. I find there is something restful oddly, in arriving at the edge of what is known and finding only open questions. It takes the pressure off. You are not failing to understand something that everyone else has figured out. You are standing exactly where the smartest people in the world are standing, looking out at the same darkness, holding the same lantern, seeing the same short distance into the unknown. And there is one more possibility we should set on the table, in fairness, before we turn to the future. What if dark energy is not a thing at all? What if there is no mysterious energy in empty space, and instead our very theory of gravity, Einstein's general relativity, is subtly wrong on the largest scales? Perhaps gravity behaves a little differently across billions of light years than it does in our solar system. And what looks to us like a strange pushing energy is really just gravity itself behaving in a way we have not correctly described. There are physicists working hard on exactly this idea, building modified theories of gravity to see whether they can explain the accelerating universe without inventing any dark energy at all. So far, none of these modified theories fits all the evidence as cleanly as plain dark energy does, and most cosmologists still favor the dark energy picture. But it remains a live and respectable possibility that the deepest lesson of the accelerating universe is not that space is full of strange energy, but that gravity has been quietly keeping a secret from us all along. We genuinely do not yet know which it is. Now let us think, slowly and without alarm, about where all of this is going. Because the nature of dark energy does not only tell us about the past and present of the universe, it writes the ending. And the ending depends entirely on which version of dark energy turns out to be true. So let us walk gently through the possible futures, the way you might consider, without any urgency, the different paths a long road might take far beyond where you can see. If dark energy is the simplest thing it could be, a true cosmological constant, the steady energy of empty space, with that number W fixed forever at -1. Then the future is one of quiet, gradual, gentle dispersal. The expansion will keep accelerating, smoothly and forever. The galaxies that are not already bound to us by gravity will recede faster and faster, their light stretching redder and dimmer, until one by one they slip beyond the edge of what we could ever see, carried away by space growing faster than their light can cross it. In the very far future, an observer in our galaxy would look out and see only an empty darkness, with no other galaxies visible at all, because every one of them would have been swept beyond reach. Our own galaxy, and the small cluster of galaxies bound to it by gravity, would remain, an island of light in an ocean of black. And then, across timescales so long they make the current age of the universe look like a single heartbeat, even that island would slowly run down. Stars would burn out and not be replaced. The last red embers would fade. Matter itself, over almost unimaginable stretches of time, might slowly decay. The universe would drift toward a cold, dark, thin, silent state, spread ever more thinly, ever closer to perfect stillness and uniform cold. Physicists call this the heat death, or sometimes the big freeze. It is not a bang and not a crunch. It is a long, slow, peaceful fading toward an eternal, featureless calm. There is something almost restful in it, if you do not look too hard. The universe does not end in violence. It ends in quiet. But that gentle ending is only one possibility, and it depends on dark energy being a true constant. Suppose instead that dark energy is one of those stranger quintessence fields, and suppose its strength is not holding steady but slowly growing over time. Suppose that number W is not exactly -1 but a little below it, what physicists call the phantom regime. Then the future takes a far more dramatic turn. If the outward push of dark energy strengthens without limit, then over time it would overpower not just the gentle gravity between distant galaxies, but eventually the much stronger gravity that holds a single galaxy together. Galaxies would be torn apart, their stars flung into the growing void. Then the push would grow stronger still, and solar systems would be pulled apart, planets ripped from their stars. Then stronger again, and the planets themselves would be torn open. And in the final fractions of the final moment, dark energy would grow so overwhelmingly strong that it would tear apart atoms, and then the very particles within them, shredding the fabric of everything down to nothing. Physicists call this the Big Rip. And in such a future, the universe ends not by fading, but by flying apart entirely at a specific moment, with everything that exists pulled into shreds by the runaway strengthening of dark energy. It is, I will admit, a far less soothing bedtime thought than the slow freeze. But I tell you about it because it is a real possibility in the equations, and it depends on a number that we are, right now, straining to measure. The good news, if you want comfort, is that even in the Big Rip scenario, the end lies tens of billions of years in the future, far beyond the lifespan of our sun, far beyond anything that touches us or anyone we will ever know. And there is a third possible ending, gentler in shape though heavier in mood, which would arise if dark energy were the opposite of phantom, if its push were instead slowly weakening, fading away over time, perhaps even reversing into a pull. Then the acceleration we see today would not last. The expansion would slow and stop and turn around, and the universe would begin to contract, all the galaxies falling back together over enormous ages. The cosmic expansion playing in reverse until everything that exists collapsed back into a single hot, dense point, a mirror image of the beginning. This is the old Big Crunch, the fate that cosmologists once thought most likely back when everyone assumed gravity would eventually win. Dark energy seemed to have ruled it out. But if dark energy is changeable, if it is the kind of thing that can fade and reverse, then the Big Crunch quietly returns to the menu of possible endings. No longer impossible after all. So there they are, the three great endings. And notice how completely they hang on the single question we have been circling all night. What is dark energy, really? If it is a constant, the universe fades slowly and forever into the cold. If it strengthens, the universe one day tears itself to pieces. If it weakens and reverses, the universe collapses back into a fiery point. The same observations of the same accelerating universe permit all three, and which one is true depends on the deepest nature of the thing we understand the least. We are, in a real sense, trying to read the last page of a book, whose ending changes depending on a property we have not yet been able to measure precisely. And it is exactly that property, the question of whether dark energy holds steady or changes over time, that the very newest measurements have begun, just possibly, to disturb. For most of the years since dark energy was discovered, as I mentioned earlier, the measurements kept pointing patiently at the simplest answer. That number W sat at -1, or so near it that no one could honestly claim a difference. And the cosmological constant, however unsatisfying, kept winning. The universe seemed content to be described by Einstein's old discarded term, and the dream of catching dark energy in the act of changing kept coming up empty. But measurement is a slow art, and it improves. And over the last couple of years, a great new instrument has begun to map the universe in more detail than ever before. And its early results have stirred something that has the whole field leaning forward. The instrument is called the Dark Energy Spectroscopic Instrument, mounted on a telescope at Kitt Peak in Arizona, and it is a marvel of patient engineering. It can gather the light of 5,000 galaxies at once, through 5,000 tiny fibers that swing into position to catch each one. And night after night, it builds the largest three-dimensional map of the universe ever made, charting the positions of millions upon millions of galaxies and quasars stretching back across billions of years of cosmic history. It is an international effort, with hundreds of scientists from dozens of institutions around the world. And the way it probes dark energy is beautiful. Hidden in the way galaxies are spaced across the sky is a faint, regular pattern, a preferred distance between galaxies that was frozen into the universe by sound waves rippling through the hot, early cosmos before the first atoms formed. That preferred distance acts like a ruler, a standard ruler laid across the sky, and by measuring how that ruler appears to stretch at different distances and therefore at different times in cosmic history, the instrument can trace exactly how the expansion of the universe has changed, and therefore how dark energy has behaved across the ages. In the spring of 2024, and then again with more data in the spring of 2025, the collaboration shared its findings, and they contained a genuine surprise. Taken entirely on its own, the new map is perfectly consistent with the old, simple picture, with a constant dark energy, with that value of WW sitting at -1. So, I want to be careful and honest with you here, but when the new map is combined with the other great sources of evidence, the ancient light of the cosmic microwave background, and the exploding stars, and the way distant light is bent by gravity, a different and intriguing hint begins to emerge. The combined data seem, ever so slightly, to prefer a dark energy that is not constant after all. A dark energy that was somewhat stronger in the past and has been gently weakening over the last several billion years. If that hint is real, it would mean dark energy is not Einstein's eternal constant. It would mean it is something more like quintessence, something alive and changing. And it would, as the scientists themselves have said, represent a genuine shift in our understanding of the universe. Now here is where I must ask you to hold this loosely, the way you would hold a candle flame, gently, without gripping. Because a hint is not a discovery. The strength of this evidence depends quite sensitively on which particular set of exploding stars you fold into the analysis. And depending on that choice, the hint ranges from fairly weak to moderately strong. But in none of these cases does it yet reach the very high bar that physicists demand before they will say something is truly established. Some careful researchers, including a respected cosmologist named George Efstathiou, have pointed out that the apparent signal might not be evolving dark energy at all, but rather some subtle systematic error in how the brightnesses of the distant supernova have been calibrated. In other words, the universe might be whispering something profound, or it might be that one of our rulers is very slightly bent in a way we have not yet noticed. The honest situation, as of now, is that this is a tantalizing, much discussed, not yet confirmed hint. Exactly the sort of thing that may, in a few years, with more data, either firm up into one of the great discoveries of the century, or quietly melt away as the measurements improve. Both have happened many times before in the history of this science. The careful thing, the patient thing, is to wait and watch. There is a second, quieter puzzle worth mentioning here too, because it has been nagging at cosmologists for years, and it tangles with the question of dark energy. It is called the Hubble tension, and it goes like this. There are two main ways to measure how fast the universe is expanding today. One way works outward from the ancient light of the cosmic microwave background, using the early universe to predict the present rate of expansion. The other way works directly in our own cosmic neighborhood, measuring the actual recession of nearby galaxies using those reliable standard candles. Both methods are careful. Both methods are precise. And the two methods give answers that do not quite agree. The directly measured local expansion comes out a little faster than the value predicted from the early universe. And as both measurements have grown more precise, the gap between them has not closed, but stubbornly persisted, refusing to go away. No one is certain what this means. It might be a hidden error in one of the methods, or it might be a real crack in our standard model of the universe. A sign that something about dark energy, or about the early universe, or about gravity, is not quite as we have assumed. It is another loose thread, another place where the beautiful tapestry of modern cosmology does not lie perfectly flat, and where pulling gently on the thread might one day unravel something, or might simply turn out to be a snag. I tell you about these unresolved frontiers, not to leave you unsettled, but to be truthful, because the truth is genuinely more interesting than any tidy ending. We are living through a moment when the question of dark energy is wide open again, when the simplest answer is being quietly questioned by the newest data, when a constant we thought we understood might turn out to be a changing thing we do not. You happen to be alive at a time when human beings are actively trying to find out whether the universe will fade or tear or collapse, and when the answer is not yet known to anyone, anywhere. That is a remarkable thing to drift off to sleep thinking about. The book of the cosmos is still being written tonight in observatories on dark mountaintops all over the world, while you lie here in the warmth, and no one yet knows how it ends. Let me bring all of this a little closer to home now, closer to the room you are in and the life you are living, because it is easy to feel that dark energy is something impossibly remote, a concern only for galaxies billions of light years away, with nothing to do with you. And in one sense, that is true. Dark energy is so faint, so gentle, that within our galaxy, within our solar system, within the space of your bedroom, its effect is utterly, completely negligible. It will never push your walls apart or stretch the distance between you and the person sleeping beside you. The bonds that hold you together, the gravity that holds the Earth, and the chemistry that holds your atoms, are trillions upon trillions of times stronger than the whisper of dark energy across such a small space. So you can rest easy. The acceleration of the universe is real, but it lives only in the vast gulfs between galaxies, and it leaves the small, warm, human scale of your night completely untouched. And yet, in another sense, dark energy reaches all the way down to this quiet moment, because the discovery of it is one of the great triumphs of exactly the kind of patient, collective, human-looking that you are taking part in your own small way, simply by being curious enough to listen tonight. Think about what it took. It took Slifer sitting alone in the cold in Arizona, night after night, reading the barcodes of faint smudges of light. It took Friedman doing patient algebra in Russia and dying before he could see he was right. It took a Belgian priest deriving the expansion of the universe and publishing it in a journal almost no one read. It took Hubble and his careful assistant Humason measuring distances at the eyepiece of a great telescope. It took Einstein being wrong and being honest about being wrong. It took two rival teams of astronomers in the 1990s, photographing the same patches of sky again and again, racing to catch exploding stars before they faded, and finding, to their own dismay, an answer none of them wanted. It took the patient mapping of the oldest light in the universe. It took thousands of people, across more than a century, each adding one careful measurement to the pile. None of them able to see the whole picture, all of them trusting that the looking was worth it. And out of all that quiet, unglamorous, cumulative human attention came one of the most astonishing facts ever learned: that the universe is mostly made of things we cannot see, and that it is flying apart faster every year, pushed by something we still do not understand. There is a thought in all of this that I find quietly moving, and I want to leave it with you before we wind all the way down. We talked about how, in the far future, the accelerating expansion will carry all the other galaxies beyond the edge of what anyone could ever see, until an observer in our galaxy would look out and find only darkness, with no sign that any other galaxy had ever existed. Think about what that means. It means that we, right now, living in this particular slice of cosmic time, are able to see something that future astronomers will not be able to see. We can still look out and behold a sky full of other galaxies, still measure their redshifts, still read in their light the whole story of an expanding, accelerating, ancient universe. A civilization that arises in the very far future, after the other galaxies have all slipped away, would look out at an empty black sky around their lonely island of stars, and would have no way of knowing that the universe was ever anything other than that single island. They would have no way to discover the expansion, no way to find dark energy, no way to learn of the Big Bang at all, because all the evidence would have been carried beyond their reach. The cosmos is, in a real sense, readable right now, in this epoch, and it will not always be so. We happen to live at a time when the universe still tells its story, when the clues are still in the sky. That is not nothing. That is a kind of fortune, a window that is open now and will, over unimaginable ages, slowly close. So the next time you find yourself somewhere dark enough to see the stars, and you look up at what seems like a still and silent sky, you might hold this in the back of your mind. That the silence is an illusion, that everything up there is drifting apart, that the dark between the stars is quietly growing, and that you are looking at it during the brief, bright chapter when it can still be understood. You are not separate from the universe, gazing at it from outside. You are made of its ordinary 5%, the rare bright foam on the dark ocean, a little arrangement of atoms that the universe has assembled into something that can look back at itself and wonder. The same expansion that carries the galaxies apart carried long ago the conditions that let stars form and planets cool and life begin. The story of dark energy is, in the end, also the story of how there came to be anyone at all to notice it. Let us gather everything together one last time, slowly and softly, the way you might walk back through the rooms of a house turning off the lights before bed, just to be sure of where everything is. We have covered a great many confusing things tonight, and I want to set each of them down gently in its place, restated in the plainest words I can find, so that even if the details have already begun to blur, the shape of the whole remains. We began with a single strange fact. The universe is expanding, and the expansion is speeding up. The galaxies are not flying through space like shrapnel from a blast. The space between them is growing, swelling everywhere at once, like the dough of a raisin loaf rising, carrying every galaxy away from every other. And the swelling is not slowing down the way everyone expected. It is accelerating. Something is feeding it. That something is what we call dark energy. The word dark just means hidden. We cannot see it. We cannot hold it. We know it only by its effect, which is to push the largest scales of the universe apart. It makes up roughly 7/10 of everything there is. It is smooth, the same everywhere, and it does not thin out as the universe grows, which is the secret of why it eventually takes over. More space simply means more of it. The simplest idea for what dark energy is the energy of empty space itself, an energy that the vacuum carries just by existing, which Einstein first wrote into his equations long ago as the cosmological constant, and then threw away in embarrassment, calling it, so the story goes, his greatest blunder. The trouble with this simplest idea is that when we try to calculate how much energy empty space should carry, our best theory gives an answer that is too large by a number with something like 120 zeros after it. The worst mismatch between theory and reality anywhere in science. So we know dark energy is there, and we even know roughly how much of it there is. But the theory that should explain its size fails by a margin almost too vast to imagine. That unsolved puzzle is called the cosmological constant problem, and it remains, after decades, unsolved. Because that simplest idea is so troubled, physicists have imagined alternatives. One is quintessence. The idea that dark energy is not a fixed constant, but a slowly changing field. Something that might have been stronger or weaker in the past, and might grow or fade in the future. Another is the possibility that there is no dark energy at all, and that instead, our theory of gravity is subtly wrong across the greatest distances. And to explain why dark energy is so strangely small, some have reached for the unsettling idea that our universe is one of countless universes, and that we find ourselves in a rare, gentle one simply because the violent ones contain no one to look. Every one of these ideas is held loosely by serious people, none of them confirmed. All of them honest attempts to explain a thing we do not understand. We learned how the discovery was actually made by two rival teams of astronomers in the 1990s, using exploding stars called Type 1, a supernovae, as reliable beacons of known brightness scattered across the depths of cosmic time. They expected to measure a slowing universe and found instead an accelerating one. And they trusted the answer precisely because neither team wanted it, and both found it anyway. We saw how that result was confirmed from completely independent directions, by the clustering of galaxies and by the ancient afterglow of the Big Bang, until the strange recipe of the cosmos, a sliver of ordinary matter, a slice of unseen dark matter, and a great majority of dark energy, became almost impossible to doubt. And we looked finally at how the whole story is still unfinished, at the newest maps of the universe, which hint, faintly and not yet certainly, that dark energy might be changing after all, at the stubborn small disagreement over exactly how fast the universe is expanding, at the three possible endings, the slow fade into cold, the violent tearing apart, the collapse back into fire, each of them waiting behind a question we cannot yet answer. The universe has not finished telling us what it is, and the people whose job it is to find out are, at this very moment, out on dark mountains around the world, patiently gathering the light, one measurement at a time. So if you take only one thing from all of this into sleep, let it be something simple and true. We live inside a vast, expanding, accelerating universe, mostly made of things we cannot see and do not understand. And the not understanding is not a failure, but an invitation. The open edge of everything still left to learn. The greatest physicists alive know only a little more about dark energy than you do now after these couple of hours. They too are standing at the edge of the dark, holding a small lantern, seeing just a little way in. There is a deep companionship in that. Between you lying here and them out there, all of us human, all of us curious, all of us looking up at the same accelerating sky and wondering. Now let the ideas begin to loosen their hold a little. You do not need to keep any of them gripped tightly anymore. Let the names drift. The cosmological constant, quintessence, vacuum energy, the equation of state, the supernovae. Let them all soften at the edges and float away if they want to. You have understood them tonight. And that understanding does not vanish just because you stop holding it. It settles somewhere quieter, the way the meaning of a long day settles into you while you sleep, without any effort on your part at all. Think, just for a moment longer, about the gentleness of the thing we have been describing. Dark energy is not violent. It does not crash or roar. It is the faintest imaginable tendency woven into empty space. So faint that across the whole width of your room, across the whole width of the earth, across the whole width of the solar system, it does nothing you could ever feel. It only becomes powerful when it is given the unimaginable emptiness between galaxies to work across, vast oceans of nothing where its tiny, patient push has room to accumulate over billions of years. There is something almost tender about a force that is so nearly nothing, and yet, given enough emptiness and enough time, quietly governs the fate of all that exists. The universe is shaped, in the end, not by violence, but by patience, by the slow accumulation of the very smallest things across the very largest spaces and the very longest times, and you are held safely inside the small, warm exception to all of it. Here, on this scale, gravity wins. The earth holds you. The bed holds you. Your own body holds together, every atom bound to its neighbors far more strongly than any expansion could ever overcome. The accelerating universe is real, and it is everywhere. But it is also infinitely far from this room in every way that matters tonight. Out there, the galaxies drift apart. In here, everything is held. Both things are true at once, and you get to rest inside the gentle one. So let your attention come back, slowly, from the edge of the universe to the edge of yourself. From galaxies billions of light years away to the simple weight of your own body where it rests. There is no distance you need to travel anymore. There is nothing left to understand tonight. The expanding universe will go on expanding whether you watch it or not, and it does not need you to keep it company any longer. It is content. And so, now, can you be? Let yourself feel the surface beneath you, holding all of your weight, asking nothing of you in return. Feel where your head rests, and let it grow heavy there. Let your shoulders sink down, away from your ears, releasing whatever they have been quietly carrying. Let your arms be heavy. Let your hands be soft and open. Feel your breath moving on its own, slow and unforced, the gentlest rhythm there is, needing no attention from you at all. Let your chest rise and fall like something tidal, something that has been happening since long before you were born and will go on without your watching. Let the heaviness move down through you now, into your hips, into your legs, into your feet. Every part of you growing warm and weighted and still, sinking a little deeper into the place that holds you. There is nowhere to be. There is nothing to solve. The great question of what dark energy is can wait for the morning, and for the patient people on the mountaintops, and for the children not yet born who will one day know more than anyone alive tonight. None of it is yours to carry into sleep. Above you, far beyond the ceiling, beyond the roof, beyond the thin blue air and the dark beyond it, the universe is drifting slowly apart, gently, silently, in no hurry at all, across distances too large to hold in any mind. And here you are, a small, warm gathering of its ordinary matter, safe and held and growing heavier with every breath, letting the whole vast, accelerating cosmos carry on without you for a while. Let your thoughts slow. Let them dim and stretch and redden like distant light, drifting quietly past the edge of what you can see. Let the dark between them grow soft and wide. And let yourself rest now, here, held in the gentlest corner of an expanding universe, while sleep comes in like the tide, slow and certain, and carries you the rest of the way down.